This is going to be a very whirlwind through various analyses that we've done of the simulations, thanking a huge amount of people. So we've got 4 or 5 speakers today in those. John and Jessica are away, so I'll fill in for them. And then this model we basically started developing at the end of 2022. We started the pre-industrial spin-up, so it's been going a long time. So the top there is just the low and the high resolution animation of some of the clouds and precipitation into the couple simulations. So this is what we're doing. So there's obviously bits I can skip. So hopefully you know what EERIE is, for example, and you hopefully know what the simulations are. And then we'll just go through some of the results that we've been looking at. Not quite in the order that is there, because I haven't reordered us for next week yet. And what's our objective? So obviously we have the EERIE perspective, the role of the ocean mesoscale. We want to understand the role of model resolution and how it impacts climate simulation, implications for future risk, planning, adaptation, etc. I think looking towards our CMIP7 simulations, I think having models in there that are not 100-kilometer and so are different. In some aspects they might be worse, but I think being different is useful, but versus the common biases that those 100-kilometer models have. We're obviously not the first people to do CMIP style simulations at these kind of resolutions, but we think we'll be the only group submitting such simulations to the CMIP7 fast track. Well, they'll be very interested in the groups that are here if anyone else is doing this for the fast track. I won't dwell on this because you know all this. So we've got a low, a middle, and a higher resolution model setup, and we've done 200 odd years of spin up, 200 years of the PI control, and then the historic and the future 2100 with SSP 245. As I say, the high resolution model, we started on a machine back in 2022 where it ran at about 0.75 years a day. On our newest machine, that's up to more like 2 years a day at peak speed. But we went from here, the start of here, I'll say, was late 2022, and we completed the future in 2025. So it was a long way. And then just to advertise, and if I have time, which I may not at the end, I'll show you the progress of these, that we are running this same model for the CMIP7 AFT assessment fast track, including a 500-year PI control, 3 historical members, 2 scenarios from those historicals, the high and at least 1 other scenario, the 1% run. We've already completed 150 years of the abrupt 4 times CO2, the AMIP and the AMIP plus 4K, a couple of these more idealized simulations, and we've actually done the high-risk AMIP simulation as well, with obviously all with the CMIP7 forcings. So I'm just going to give a very brief overview of the mean state and the radiative fluxes. So just to give some background to anyone, so when we did the tuning back in 2022, we used 1 tuning parameter for the different resolution models, and it was this thing. And this basically changes the cloud inhomogeneity and hence the amount of shortwave that reaches the surface. So that was our only tuning knob to get the TOA to 0 in the pre-industrial spin-up. So because that changes the shortwave, basically we're only tuning the shortwave. And so as we know, as we increase the ocean resolution, the ocean surface tends to warm up and the outgoing long wave increases, but the only tuning we have is for the shortwave. And so hence, if we look at the SST bias from the low, middle, and the higher resolution, this is at the end of the historical simulation, you can see that the high resolution model is quite warm. So it has quite a significant warm bias. So it's quite warm in the tropics, but also at kind of mid to high latitudes compared to the medium and the low. And in fact, the medium, which is where we do most of our model development, you would say the biases look much better in the medium resolution than the high resolution. But the way we did the tuning is the reason why that's the case. And that effectively we had to tune down the amount of outgoing shortwave because the amount of outgoing long wave increased. And so therefore we end up with a warm SST. I won't dwell on the outgoing shortwave and long wave biases, but they basically follow that SST. However, it's definitely a warm bias model. But if we look at the seasonal climatology across a range of metrics across the whole of the CMIP6 archive using the PCMDI metrics package, then the low, middle, and high are the 3 simulations at the end. And as you can see, they look pretty good. So compared to the whole CMIP archive, these are normalized. So blue means considerably better than the CMIP6 median. These are pretty good. So the biases, although that was quite a warm bias, you could imagine some of these biases must be pretty bad if that warm bias model looks this good in terms of the root mean squared. Then if we can look at the variability, so these are different modes of variability. Harley will talk a bit more about variability in a minute, but as an overview, we know the southern annular mode is poor because the Antarctic is very warm. But in terms of the other modes of variability, again, the model looks pretty good. It's pretty reasonable, definitely within the pack, if not as good as any other of the CMIP6 models. And the ENSO, similarly, it's not outstanding, and obviously there are papers being written on the ENSO now. But again, the last 3 rows here, it's definitely competitive with the CMIP6 archive. I won't dwell on this because we know that as you go to eddy-rich modeling, you get the eddying and the variability in the right places and about the right magnitude. And I won't really dwell on this either. So Aaron is doing much more robust metrics of these coupling of thermal and mechanical. But I think it was worth, again, noting this was from the first year or 2 that Deanne triggered. If you look at the daily anomalies of SST and wind speed, then going from low to middle to high resolution really fundamentally changes the small scale coupling between the atmosphere and the ocean, and you get much closer to the observations. Whereas if you look at the large scale, it doesn't really change. So the kind of large scale coupling, which is mostly atmosphere driving ocean, doesn't change. And tropical cyclones, so again, the models look pretty good in the Atlantic and the Western North Pacific. Perhaps we don't get such high numbers as we see in the observations, but the variability looks pretty interesting. And we do find as we go into the future that the intensity slightly increases in the Atlantic and kind of more visibly increases in the Western North Pacific, probably as you'd expect. And then maybe I'll hand over to Michael.
Okay, thank you very much. Can everyone hear me?
Yep.
Okay, yeah, so I'm going to talk a bit about the historical and future surface air temperature and the differences between the resolutions and the possible causes of why they might be different. So this plot is the surface air temperature anomaly time series. Blue is the low resolution, red is the medium, and green is the high resolution. You can see that in the historical period, the blue, the low resolution, seems to have more stronger variability than the other resolutions, but all the models match the observations pretty well until about 2000s, and the LL becomes a bit warmer, and that difference extends all the way to 2100 under the SSP 245 scenario. The low resolution ends up being about 1 Kelvin warmer than the high resolution at the end of the century, with the medium resolution sitting in between. And this is potentially quite an important feature to understand, as the Hadgen model traditionally had quite high climate sensitivity in the CMIP6 models. So going to higher resolution and changing the warming trend might be might be one way of changing the climate sensitivity. Can you move to the next slide, please, Malcolm? So we only had the resources to run 30 years of the full-time CO2 at the high resolution. And so this figure is a plot of the climate sensitivity calculated with increasing years. So the number of years used for calculating the ECS is shown on the x-axis, and the y-axis is the ECS for that length of simulation. So normally it's calculated at 150 years. So you can see that for the LL and MM, you get a sort of pretty good idea by about year 60 of what it'll end up being. So for only 30 years of the HH simulation, we see that it has a much, much lower ECS than the other resolutions. So we wanted to understand a bit why that is. Can you change the slide, please? Next slide. One worry is that it might be related to the too low CI bias in HH. So Malcolm talked about the high resolution model being quite a bit warmer, and that manifests also in low CI bias in the high resolution model, especially at the Southern Ocean. So you can see on the left-hand side, especially in the Weddell Sea, the HH has much less CIs than the other models, and that's related to polynyas and so on going on in that area. So one worry is that this too low CIs means there's less ice being available to melt. So the positive surface albedo feedback is weaker, and therefore the warming trend is weaker. So this might be getting a low ECS for the wrong reason. So we wanted to check whether that's the case or not. Can you flick to the next page, please? So we do this using the APRP methodology. I'm not going to go into details of it, but the APRP basically helps you decompose the radiative terms into different processes, so you can better estimate which processes are stronger, and you can estimate the feedbacks better than just using the raw model outputs. So I'm using the APRP to calculate the feedback parameter associated with the surface albedo changes, which is related to sea ice changes, and then substituting it back into the main equation to find how much temperature change that partial feedback parameter is responsible for. Next page, please. So this is a regression of the shortwave changes due to surface albedo regressed onto the surface air temperature to calculate the surface albedo feedback parameter. So in HH it's about 0.27, while in LL it's 0.3. So we get a weaker positive feedback in HH, which is what you would expect, because we have less sea ice to melt. So how does this translate into actually the delta T? Next page, please. So substituting this back into the temperature, the equation telling us relating feedback and forcings to delta T, we can see that so if you have a lambda, the total lambda, say is LL, lambda albedo of 0.3 gives you 0.345 delta T per decade, which translates to about 4.17 Kelvin at year 2100. So if you take away 0.03 in the lambda parameter, so if you shifted the blue line a little bit to the left, you would ultimately get 4 Kelvin at year 2100. So it only explains about 0.15 Kelvin at 2100, which is only a fraction of the 1 Kelvin difference we saw earlier in the time series. So basically, overall, the CI's biases and its effect on the radiated feedback is not enough to explain the difference in the 2100 surface air temperature between the resolutions, which is good news because it means that the CI's bias is only having a small impact on the radiative feedbacks overall, which doesn't mean that it's not important. So maybe ocean heat uptake is the other big explanation for the differences in the resolution, but we haven't looked into that yet. So yeah, so far the lower climate sensitivity seems to be because of something else rather than a low sea ice bias. And that's me done.
Great, thank you very much. So John gave me a slide, so I think some of you will know some of this, but for our phase 1 EERIE simulations, we generated about 2 and a bit petabytes of data. For the CMIP7 fast track runs, that's going to be more like 10 petabytes, of which we'll publish about 5, which we think will be about a third of the whole CMIP7 archive size. So it's a bit of a challenge to deal with that data. But yes, and because obviously John was away, again, thank you to the DKRZ people for taking the lead on the data. And yeah, the intake catalogs and things have been really, really important for using the data. Ruth, are you online? No, maybe not. Okay, so I'll try and take you through some of Ruth's analysis of the extratropical storms. So kind of slightly curiously, we're still trying to puzzle this out. If you look at the extratropical storm frequency in the northern hemisphere, I think, or this is global, sorry, global. The medium resolution has considerably more storms than both the low and the high resolution, which we don't necessarily quite understand, and we're still, I'd say, still trying to puzzle that out. It does vary by season, but it's a kind of curious result. It doesn't matter which, the PI control or the historical or the scenario, they're all kind of similar numbers. And you can see that they all do have a decline in the number of storms into the future scenario. Perhaps as you'd expect, the maximum intensity of the storms increases as you increase the resolution. So you kind of shift the distribution. And you could argue maybe ERA 5 is not the best at saying what the real intensity of the storms are. And in terms of the track density, compared to ERA 5, which is here, you can see the low resolution has rather too many storms on the eastern seaboard, and as we increase the resolution, that distribution generally improves. The model actually does seem to be missing storms over high orography, and we do have too many over the ocean. And there's kind of question marks about the lifetimes of the storms as well. In terms of future changes, we get, probably as established by previous work, fewer storms in the Mediterranean, actually more storms in the North Atlantic, and then there's a bit of a poleward shift in the Western North Pacific. Okay, Steve, are you online?
So yeah, just a quick sort of summary of the work I was doing using the MOAP feature tracking tool. So MOAP stands for Multi-Object Analysis of Atmospheric Phenomenon, which was published a couple of years ago by Andreas Prine. And this basically just takes a set of standard climate model outputs and can identify up to 15 atmospheric features simultaneously. So we've just been running this algorithm with the 3 different configurations of HAGEM. I'm only going to present results from the low and the high res just in the interest of time. Yeah, I should say I was looking at a 10-year past period, just to try and provide some sort of consolidated time period. And I also looked at a future 10-year period as well. But again, in the interest of time, I'm only going to show results from the past period here. So, and the main result themes, I guess, I've just been looking at the like a summary of the track features in each configuration of the model, the differences between the models, and then trying to attribute the precip extremes to those track features. So just starting with so this is a summary of all the features tracked basically by MOAP within the high-res model over the past 10-year period between 2000 and 2009. Note that the color scales vary here, but don't worry too much about the details. This is more just to give like an overview of the MOAP outputs, really. I mean, I will go through them sort of row by row. So on the top row, we've got pressure systems, surface cyclones and anticyclones and their mid-level variants, and then cut-off lows as well, which are obviously also low pressure systems, but they seem to be the rarest in this family of features. In the middle, we've got other features which are a bit more complex, which are diagnosed using different model outputs besides pressure. So we've got tropical cyclones, jets, fronts, atmospheric rivers, and then MCSs. And then the bottom set of features are basically all equatorial waves, which are tracked within a few degrees of the equator. So those are the high res results. For the low res equivalents, I've calculated the difference basically relative to high res. So this plot represents high minus low. So red areas represent more features being diagnosed in HH, and blue is the opposite, so more in LL. And again, just running through the rows quickly, just picking out the interesting things. So we're seeing actually here an interesting sort of pattern where the mid-level cyclones are less frequent in HH in the northern hemisphere, and then the opposite seems to be true for mid-level anticyclones. Interesting also for cut-off lows, which are low pressure, obviously. So that's a bit of an interesting one. The middle row, again, fewer tropical cyclones in LL, but a lot more fronts, which is something we've noticed is a result that other studies have also corroborated. So jets and atmospheric rivers, you could say, are pretty much balanced in terms of the number of features. And then on the right, the MCSs are much more common in HH. And in fact, in this work, we didn't notice, or rather, that there were no MCSs diagnosed at all in the LL outputs, which is we wouldn't necessarily expect there to be none at all, but it's possibly something to do with the settings in the tracking algorithm. But there are similar studies which have shown, far fewer MCSs, in their low res equivalents. So in some ways, this result's probably not too far from the truth. And then on the bottom row, it's a pretty sort of consistent picture that the equatorial waves are all less commonly diagnosed in the high res model. I'm only really offering observations here because I haven't had too much time to look into the explanation. So, sorry about that. And then, so what does the extreme precip look like when we attribute it to the aforementioned features which MOAP tracks? So this result shows the feature which is most frequently, or rather contributes the most rainfall to the RX1 day, which is calculated over the same 10-year period. So in the high-res model, a lot of the RX1 day events can be associated with MCSs, which you might expect. Elsewhere, there's varying contributions from different features, but jets and fronts in particular seem to be quite dominant. In the low-res model results, obviously, we didn't see any MCSs tracked at all, so we wouldn't expect them to contribute to RX1 day, which is what we see. And instead, we get a lot of equatorial waves kind of filling in the tropics. Elsewhere, we see a kind of even more of a predominance of fronts, which again corroborates with the feature frequency plots, where we're just seeing a lot more fronts in the low res model. So that kind of tallies up with what we expect, really. But a question going forward, I think, from this was what, if the low res model is not representing MCSs, either very well or at all, is there some sort of implication for the actual extreme? How does that affect the extremes? How does that affect RX1 day? So what I've done here is to calculate the difference in RX1 day between the two model configurations, again over the same 10-year period. So here green values show where RX1 day is higher in the high res, and brown again is the opposite. So it's actually more of a balanced picture than we might expect. As we said, the high res model is producing MCSs or representing them, whereas the low res model doesn't seem to be, and therefore we might expect the high res model to produce just higher, rainfall totals, higher RX1 day. But as I said, the picture does seem to be a bit more balanced than that. But in fact, similar results. So this was in a paper published by Chang et al. Recently. A different time period. So there's 30 years here, but the last 10 years of this period overlaps with ours. But basically, the picture's a lot more one-sided in their case. So they're seeing a lot more greens than browns, which is intuitively, kind of makes sense somehow. But again, yeah, different models, different periods, so it's hard to take too much away from that, really. But yeah, that's just there for interest. What I've done here is so this is the same set of data now as on the left, but we've sort of tweaked the color scales a bit and unmasked the oceans. So now we're seeing that actually, our high res model is producing much higher RX1 day totals, but only generally over the oceans. And then when we compare this with the actual the frequency of the MCSs as detected in HH, which is what this plot on the left shows, there's obviously a pretty good correlation between the MCS hotspots and the places in the globe where RX1 day is much higher for HH than LL. So I think my questions, my takeaways from this really are, if in the spots over land where the low res model is producing similar RX1 day totals to the high res one, but using different mechanisms, so presumably equatorial waves or fronts or jets or something, is this realistic? And then secondly, in the regions over the ocean where it's where the lack of MCS is causing, lower RX1 day totals than the high res model, is this important? Does it matter from an impact point of view or more of a modeling point of view? Is the energy balance, in the model sort of correct? So yeah, that was. I'll leave it there. But that was pretty much the takeaway from the sort of limited investigations I've done into this. I'll stop sharing there, and hopefully Malcolm can reclaim.
Brilliant. Thank you very much. Yeah, so over to Harley.
So yeah, I'm going to quickly talk to you about the influence on model resolution on the climate variability within the HAGEM GT5E simulations, and maybe the consequences that has for the NEO. Oh gosh, okay, animations. Okay, so quick overview. Obviously, the NEO is a dominant driver of European winter climate, and it makes its prediction very important. Currently, seasonal forecasts are limited by a signal-to-noise paradox. And what that basically means is the fact that your ensemble mean better predicts the observations than each ensemble member. So the point being that your member in your ensemble doesn't have enough. Essentially, the signal for the NEO isn't strong enough. There's too much noise. And when I was looking at these simulations, the big thing was just focus on an NEO and hopefully we'll see a difference, and we don't. So there's no real major change across the spatial distribution of the NEO, really, across resolutions. And then looking at the time series of the NAO index, you don't really see any major change either. So really, the summary is the NAO doesn't change significantly across model resolution, but of course, there's a lot more to look at in these simulations. So I then went on to look at the ENSO, and you can see here a composite of the Nino 3.4 sea surface temperature anomalies. And here you can see the biases against the ERA 5 observations, well, the ERA 5 data reanalysis. And you can see that there is a warm bias in the east of the Pacific Ocean in the low resolution, and then that improves across resolutions. And your bias is generally quite minimal, I think, in the high resolution. So, you know, we can sort of say that model resolution maybe improves the Nino biases. As well as that, looking at some other statistics on the ENSO, you can see that its amplitude generally decreases across model resolution. You can also see that the duration shortens quite a lot as well. So the color is, you can see in the top right what the color corresponds to. So yeah, your duration of your events gets shorter, as does the how often the events take place. They take place more often. You also have much stronger seasonality. So overall, your ENSO is less variable, more frequent, matches the observations better, but it's weaker. And I think that's interesting because your ENSO biases may improve with increased resolution, but in general, your ENSO is weaker and doesn't last as long. And it's far less variable as well. So then we're looking at the QBO, another tropical sort of teleconnection into the NAO. And you can see here that there's not massive changes in the QBO descent height. And maybe this is more of an easy one to look at. This is the histogram of the QBO cycle duration. And you can see that actually across the model resolutions, your QBO duration is smaller. So you have, shorter QBO periods. Not by much, but it does change. So another point to take is your QBO duration shortens with increased resolution. So the question is, how do all of these changes then affect the NAO? Because we haven't seen much change in the NAO itself, but maybe we have a change in the signals that may potentially drive the NAO. So here is a composite of the ENSO teleconnections in the surface pressure. And there's lots to see on here. So the top row is just your planar composite. The bottom row is by normalizing the composite based on the strength of your ENSO. The reason being that you saw earlier that the ENSO strength reduces massively in your higher resolution. So the point being that for each degree of signal, what is your teleconnection look like? And then I've got some metrics as well. So your dashed box is where I have calculated the EOF. The EOF, you can for the NAO, you can see in the contours. The color map is the strength of the teleconnection composite, I guess. And then I have some numbers. So NAO corresponds to this little box minus this little box. So your very standard NAO index. Total amplitude is the integrated power within the dotted box. So it's kind of saying like how much teleconnection power do you have in this region. NAO-like amplitude is if you project the contours onto the color map. Pattern is if you normalize both the contours and the color map to 1 and then project them onto each other, sort of telling you how similar are the patterns instead of just looking at the strength. And then you've got a number there for the minimum in the Aleutian low. And the reason I've done all of this is because I'm trying to understand, is your teleconnection getting stronger or is your teleconnection pattern improving? So what's really driving a change in your NAO indice? And you can see across from low, medium to high resolution, you can see there's an improvement in, there's not really a strong improvement in your pattern, but there is definitely an improvement in the total amplitude in the teleconnection, and also your index is getting stronger. But when you start then looking at per degree of ENSO forcing, you start seeing these really strong changes. So you go from the low resolution, each degree of ENSO sort of forcing a minus 1.4 index, whereas each degree is forcing a minus 4 degree index. So what you're starting to see is actually the teleconnection is improving without there being any, which isn't due to a stronger forcing. So the pathway from the NINO 3.4 location to the NAO is more efficient, better. There's some stronger pickup, something's taking place. And the other interesting thing is your elution low is weakening, which, yeah, I don't know what that necessarily means, but I think that may be tied to some of this. And then moving on to then the QBO teleconnection, you can see very similar numbers and they're calculated in the same way as I described previously. However, what's interesting is you can see that your QBO teleconnection is only really captured in your high resolution, meaning that some sort of stratospheric pathway has improved with increased horizontal resolution, but I'm not quite sure what that is. So to quickly summarize, your tropical teleconnections into the NAO have strengthened with resolution. So if your NAO variability doesn't change, so your NAO noise in the simulations perhaps remain the same, but your tropical teleconnection signal strength improves, the question is, what are the consequences of that on the signal to noise paradox? So perhaps these simulations suggest that this model resolution could improve or perhaps help solve the signal to noise paradox. But there's a lot more work to go into it before I can say that confidently. But yeah, I will pass on.
Brilliant. Thank you very much. Okay, I'll try and whiz through Jessica's marine heat wave work. So Jessica, I think was the end of last year, she stopped doing this to move to a permanent post here at the Met Office. And thank you to Aaron and Emma for both the package that we used to do the marine heat wave and very much advice on doing the analysis, as we kind of know that. So this MARIX package is beautiful to use to identify and track the marine heat waves. The steps are here, but Emma is writing a paper, so you'll be able to read all about this relatively soon. There are questions about kind of how to do the baseline for this kind of thing for present day and future. There's various metrics that you can look at for the marine heat waves. But just to kind of do the top level summary. So what we find in terms of frequency is that as we increase the resolution, we seem to get better agreement in frequency compared to observations. In intensity, things also change. And I think the summary is that the low resolution model tends to have fewer marine heat waves, but when it does have them, they tend to be more intense on average. And so we think, in digging a little bit into this, that there are the mixed layer depth is implicated in that. It seems to be that the low resolution model typically has shallower mixed layer depths, and therefore it kind of warms up more and becomes a more intense marine heat wave, just because that heating is more localized at the surface. Whereas in the high resolution model, the mixed layer depth maybe is deeper, but also you obviously have the eddying that can break up and move that heat around as well. So we, as I say, we find the low resolution has fewer events, but does tend to have more intense events when it does have them. We think that's largely attributable to differences in the mixed layer depth. And therefore, yeah, as you increase the eddying in the model, then you improve those redistribution of heat. But if I can get all of Emma's diagnostics, then hopefully she can kind of give us a much better story of that. I won't dwell at AMOC either, because there's lots of analysis ongoing with AMOC, but I'd like to just note somewhat kind of still amazing to me. So I was just plotting this for our model description paper that's two or more years in the making, copying some of the observations from the Griffiths GFTL paper. And so this is the Trenberth 2019 in black, northward heat transport with latitude. And then the green is the high resolution model. And you can see I've never, ever seen a model agree with observations quite that well. So that's kind of really, really interesting. And if you look at the variability, again, the variability is pretty good. So this is kind of heat transport rather than volume transport. We tend to, I think, focus on the volume transport of the AMOC, but I think heat transport is also key for European climate in particular. Yeah, so the model maybe is slightly too high, but is pretty good in terms of latitude distribution as well. I think we're going to skip this because, again, there's ongoing EERIE analysis on the OSNAP, but this is stuff that Michael did a little while ago. I guess the one thing to note on this, and yeah, chip in, Michael, if you want anything to say, is that kind of it's interesting that at the rapid section, both the heat transport and the volume transport are pretty good, but by the time you get to OSNAP, the high resolution model definitely has too much northward flow in the AMOC. And so there's kind of a question, well, what is it about the model that you get the right things at 24 north, but too much at kind of 40, 50 north? And so there's kind of a slightly unanswered question there, which I think comes back to some of the surface bias plots in that we have this too much warming in the mid to high latitudes in the model. But the tropics and the processes, particularly in the ocean and the tropics, are far better at higher resolution. So there's kind of this, what are we doing that's not quite right? Are the models so tuned for the low resolution transports that we're kind of missing something there? So yeah, a reminder that we're running the CMIP7 fast track. And so this is just the fast track simulations that we're doing. We've completed the atmosphere only, at least the one member of the atmosphere only simulations, both the monthly AMIP and plus 4K, as well as the daily SST and sea ice from high-res MIP. And then the coupled simulations are ongoing. The 4 times CO2 has completed 150 years, but these other ones are ongoing. And we're hoping to get the first future scenario done kind of October time this year, the first historical, hopefully, by next month. So in summary, so this was the take-home message from each person, and maybe I'll just leave that on the screen. Wow, and we did it in 50 minutes. Well done, everyone. Thank you very much.